Hello, today we see how to factorize large numbers with quantum mechanics. Factorizing large numbers is a very hard problem for classical computers. In fact, encryption systems are based on this difficulty, and the keys to decrypt are basically factors of these large numbers, and if you don't have those factors, you have basically no chance to get them with a classical algorithm. This is why we need quantum computers to break encryption. We can use Shor's algorithm to factor large numbers. Let's see how it works. We have a number n to factor, and we guess we take a random number between 0 and n, let's say a. Now we compute the greatest common divisor of a and n, and it is very unlikely that the greatest common divisor will be different from 1 if a is a large number. But if we find a greatest common divisor different from 1, then we have found a factor of n. We divide n by that factor, we will get n prime, and we repeat the procedure. Anyway, we will get at some point, if not right at the beginning, a number a such that the greatest common divisor is 1. At this point, what do? Well, the best thing is not to throw away a and guess another number, because, as I said, it is very unlikely to get a factor of n. So we exponentiate a squared, and we compute the remainder of the division by n. Obviously, if a shares no factors with n, any power of a will not share factors with n. So there will be some remainder. Let's say the remainder is r. Now if r is equal to 1, we stop. If r is different from 1, we take another power, a to the cube, and so on. In the end, we will get to a power ak, which is equal to 1 modulus n, and this means that the remainder of the division by n is 1. Why by repeating exponentiation we will arrive at 1? We will see it in a moment. Now, if we arrived here, we found this power k, then we can write a to the k equals some multiple of n plus 1. And so we can write a to the k minus 1 equals mn. Now we can separate this in two factors, a k half plus 1 and a k half minus 1 equals mn. And at this point, if k is an odd number, this will not be integer, so this tells us nothing, and we have to repeat to find another a such that k is an even number, because if k is an even number, these two will be two integer numbers. So at least one of them shares factors of n, or a mixture of n and n. Point is, all the factors of n must be here. So we compute the greatest common divisor between this and n, and between this and n, and we find the factors of n. So we broke encryption. And the problem is that finding this k is very difficult for classical computers, and this is where we need quantum computers. First of all, let's see how we can be sure that by repeated exponentiation we will get back to 1 at a certain point. This is because of modular arithmetic. You know, when you do modular arithmetic, you are in the set Zn. It is modular arithmetic modulo n, and it is made of the elements 0, 1, 2, and so on up to n minus 1, such that when you do addition, you get the cycle 0, 1, 2, 3, and so on. Then when you reach n minus 1 and you add 1, n minus 1 plus 1 goes back to 0. So you do addition in this cycle, and so you get a cyclic group under addition. But when we do repeated exponentiation, we are doing multiplication modulo n, not addition modulo n. So let's see how multiplication modulo n works. Now these are all the possible reminders from division modulo n. So we need to check that multiplication modulo n is indeed well defined, which means if we take two numbers which have respectively reminders R1 and R2 by division by n. For example, you would take mn plus R1. This has remainder R1 if you divide it by n, and you take a number n prime n plus R2, which has remainder R2. These correspond to inside here to R1 and R2, and we must check that if we multiply them, we will get indeed a number which has remainder R1 times R2, so that multiplication inside this set is like doing multiplication of these numbers, and it is easy to check that this is the case. In fact, this times this is a multiple of n, this times this is a multiple of n, this times this is a multiple of n, so we only remain with R1 times R2, so we have the result m second times n plus R1 R2, and this has the remainder R1 times R2 when you divide by n. So we checked that multiplication modulo n is indeed well defined. Modular multiplication is quite different from modular addition though. In fact, you see that modular addition is a cyclic group, right? You can go from any number to any other number. You can't do the same with multiplication. Multiplication is not a group. In fact, if you take, for example, the set of integers modulo 4, 0, 1, 2, 3, you see that while with 1 and 3 you can go anywhere. For example, 1 times 0 is 0, times 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, and the same you can do with 3. If you take instead the number 2, you see that 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 0, again 2 times 3 is 2, and you get stuck in this cycle, so you'll never get to the identity. If you take, for example, let's say the integers modulo 6, 0, 1, 2, 3, 4, 5, you can easily see that the number 2 is stuck in this cycle. It goes to 4, then to 0, and so on. And also the number 4 is stuck on the same cycle. It goes to 0, to 2, to 4, and so on. The number 3 is stuck in this cycle. It goes in 0 and in 3. And you see that they can't go to the identity. Only the numbers 5 and 0 goes to the identity 1. In fact, if you only consider the numbers 1 and 5, this group 1 and 5 is isomorphic to 1 minus 1 with multiplication, where 1 corresponds to 1 and 5 corresponds to minus 1. You see that this is because 2, 3, and 4 share factors with 6. To see this better, let's consider the integers modulo 14. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The only numbers we share no factors with 14 are 1, 3, 5, 9, 11, 13. And if you take any one of these numbers, you will get to any one of these numbers, and they do form a group under modular multiplication. You see that if you take a number which divides 14, for example 2, it will skip the numbers which do not contain 2 as factor, and you will arrive to 14, and then you repeat the cycle and you have skipped all these numbers and you will never get to them. And the same thing with 7, which is another divisor of 14. But even if you take a number which is not a divisor of 14 but it shares factors with 14, you see that 4 goes to 8, then it goes to 12, then it goes to 2, then it goes to 6, then it goes to 10, and then it goes to 0, and then it repeats the cycle, and it has skipped all these numbers. And you see that in general, if you take a number a, which is a divisor of n, this number will get to 0 in the first cycle, having skipped all the other elements. And if you take a number a which is not a divisor of n, but it shares factors with n, it will not reach 0 in the first cycle, but it will reach 0 in the second cycle, or maybe in the third cycle, but it will reach 0 before touching all the elements which do not share factors with a. So we see that when we get a number a whose greatest common divisor with n is 1, it belongs to the group of multiplication modulo n, and we can do multiplication modulo n with a. So when we do exponentiation of a, we will get an element of that group. So since a belongs to the multiplicative group, there is indeed an element of that group which will map it to the number 1. But how do we know that such an element is a power of a? Because if a to the power of k equals 1, it means that its inverse is a to the k minus 1. How are we sure that its inverse would be a power of a? Let's see. Let's take a in this cycle and we compute a squared. So we have computed a, 1a squared. Then we multiply again by a, we get to a cube and so on. In the end, we must get to a power a to the m, which is greater than n. So we will get back in the cycle with the power a to the m. Now, either this power a to the m is one of these other powers of a, or it is a new element of the multiplicative group. First, consider the case in which it is one of these powers. Then a to the m is equal to a to the q plus n, because we have done the cycle. And then you can write n equals a to the m minus a to the q. And then you can factor out a to the q like this. So you have that a to the q divides n. But if the greatest common divisor between n and a is 1, e to the q must be 1. So if you get to a power of a, if you get to an element of this set, you must get to 1. Now let's consider the second case in which you get to an element b which is not a power of a. You keep multiplying by m, so you compute a to the m plus 1, which will be b times a. Then you compute a to the m plus 2, which will be b a squared. Then you will have b a cubed and so on. In the end, you will get to a power which is greater than n, and if this new number c, which is greater now than 2n, because you are doing the cycle 1 times more, either c is a power of m, or c is not. If it is a power of m, as we have seen before, it must be 1. If it is not a power of m, it will be another number c, and then you keep multiplying by a, you will get ac and so on, and you will get to another cycle, you will get to another number d and so on. The point is that we have a finite set, so we will run out of elements, and so we will have to get back to 1 sooner or later. So there must be a power k such that a to the k is 1. K is called the order of a, and why finding the order of a is difficult for classical computers, it takes a long time to do that, quantum computers can do this very, very fast. What is exactly the power of quantum computers? How do they do that so easily? Quantum computers take as input all the possible guesses. Then they do the computations in superposition, and if the algorithm is well made, the wrong answers will destructively interfere, so that at the final measurement you will most likely get the correct answer. Spooky, isn't it? So the idea is this: we will have a gate MA which performs modular multiplication by A, and so it will send the state psi to A psi. Now let's study the eigenvectors to this. So the psi 0 such that it is equal to some eigenvalue lambda times psi 0. We see that an eigenvector is 1 plus a plus a squared up to a to k minus 1 divided by square root of k for normalization. And you see that it is an eigenvector because if you multiply these by a, then you get a plus a squared plus a to the cube and so on. Then you get here, and this times a is 1. So you get exactly the same vector. You just permuted the order of the elements here, and so it is an eigenvector with eigenvalue 1. Now our intuition is to associate modular multiplication to arithmetic on the complex cycle. So that we associate modular multiplication to summation on the cycle. So the complex cycle is the set of the numbers 2 pi I theta with theta between 0 and 1, so that if you take e to the 2 pi I divided by k, you see that if you take the kth power of this, you go back to 1. So we will associate this to a, and this is the order of a. And there is a compact notation for 2 pi I divided by k, which is omega k. So we define omega k equals e to the 2 pi I divided by k. Now let's consider a state psi 1, which is like psi 0, but every element here is shifted by a phase, and this phase is a power of omega minus k. Omega minus k is e to the 2 minus 2 pi I divided by k. So psi 1 is equal to 1 plus omega minus k a plus omega minus k squared, a squared, and so on up to omega minus k to the k minus 1, a to the k minus 1, so that the power of omega matches the power of a inside the ket. Now let's apply MA. So let's multiply everything here by a. So this will be a, this will become a squared omega minus k, and so on. So you see that a before had omega minus k, now it has 1, so it has been multiplied by omega k. Remember that omega minus k is the inverse of omega k. So it is the same with all the others. So which is that this is an eigenvector with eigenvalue omega k. In general, you can see that you have eigenvectors psi m, where you replace omega minus k with omega minus k to the power of m, so that aj will be multiplied here by omega jm, omega minus k jm. Basically, you take the nth power of every omega minus k, and it will have eigenvalue omega k to the power of m. So we have these eigenvectors psi m with eigenvalues omega k to the power of m, which is this phase shift here performed by the matrix, by the gate MA, and m divided by k is a phase theta between 0 and 1. And if we had an algorithm to evaluate theta, we could get the fraction m divided by k. Can we build such a circuit which will give us theta for sure? That circuit will entangle the phase theta with some bits, so we will get in the end a binary approximation of theta, let's say some number b divided by 2 to the n, which is a binary approximation of m divided by k. Of course, we want to get 1 divided by k, not m divided by k, but in which case we would put the eigenvector psi1, but the point is we don't know which eigenvector is psi1, which eigenvector will have eigenvalue omega k to the power of 1. So what we can do is input a superposition of these eigenvectors, and we will have a random result, a random fraction, m divided by k. This is not a problem because there is a quite efficient classical algorithm. It is the continued fraction algorithm, which allows us, given a binary approximation of m divided by k, to find the closest fraction to this binary approximation. The problem is when m shares factors with k, in which case we would get a reduced fraction n prime divided by k prime, and we will not get k. So all we can do is to input a superposition of all the possible guesses, so of all the possible eigenvectors, and we will get a random result m divided by k. Then we repeat the algorithm and we will get another random result for another m divided by k. So in the end we will take all the possible values of k. We will compute the least common multiple between all the values of k, so we will get the greater value of k, which will be indeed our order. And we need a uniform superposition of all the eigenstates to get a random sample, and we can get a uniform superposition by inputting the ket1, because the ket1 you can check by the expressions for the eigenvectors is the summation psi0 plus psi1 and so on up to psi k minus 1 divided by the square root of k. So ket1 is indeed the superposition of the uniform superposition of all the possible eigenstates. So we input 1, we put it in a circuit which perform these operations. Here we have other bits and they will be entangled with controlled operations, so that we will measure these bits. Here we will get a random result which will be a binary approximation of m divided by k. Then we will perform the continued fraction algorithm. Then we will get all the possible denominators k, and we will get k, our order, by computing the least common multiple between all those k's. So let's build this circuit. We need 3 basic components, which are the Hadamard gate, or the Hadamard gate, and this basically takes the ket0 and the ket1. It takes 0 in a superposition of these two kets, 0 plus 1 divided by 2. It brings them in uniform superposition. So this is performed by the matrix 0 goes in 1, 1, and 1 goes in 1 minus 1. So this is the matrix, the Hadamard matrix, and we need this in order to get all the possible digits 0 and 1, or the possible values 0 and 1 for each digit. So we will output 0, then we perform an Hadamard gate, and we have a superposition of them, and so on, so that all our zero here will represent binary digits, and these binary digits will be entangled with the phase, so that when we measure them, we will measure a binary approximation of the phase. Then we need our matrices MA, and these matrices perform multiplication modulo A, and so they will send our psi to lambda psi, where lambda is the eigenvalue, which is omega minus k to some power of m, and remember that this is e to the 2 pi I m divided by k, so it is not a minus, and we have called this m divided by k theta, and this is the phase which we want to evaluate. Then we need a gate which performs the quantum Fourier transform. The quantum Fourier transform is similar to the classical Fourier transform, but it is a matrix, so it is a summation in the kets x and y, which with x goes from 0 to n minus 1. This is the quantum Fourier transform of order n, and y goes from 0 to n minus 1. The coefficients are e to the 2 pi I xy divided by n, and it is normalized, so you have 1 over square root of n here. In fact, if you apply this to a particular ket y, you get fn on y equals 1 over square root of n, summation for all the possible x of e to the 2 pi I x times y divided by n times x, which is what you would expect from a Fourier transform. To get familiar with the quantum Fourier transform, we can compute f1. For example, f1 is clearly 1. Then we have f2. f2, we have components when x and y are equal to 0, when x is equal to 0 and y is equal to 1, then 1, 0, then both equal to 1. And in this case, we have 0 times 0, so we have 1. And also in this case, we have 1, because if one of them is 0, then this exponential is 1. And instead, when they both are 1 and 1, this component, we have 2 pi I divided by n, and n in this case is 2. So we have e to the pi I, which is minus 1. And we get this matrix. So this is F2. And we see that it is exactly the Hadamard matrix. So what we want to do is, using Hadamard gates at the beginning before entangling the digits, then after we have performed the computations before the measurement, we use quantum Fourier transforms. We can write this in matrix form as fn equals 1 over square root of n times the exponential of 2 pi I divided by n times this n by n matrix. And here we have 0 times 0, because here we have x times y, 0 times 1, which is 0, and so on. So inside this matrix, we see that here we get all the 0, here we get all 0, here we get 1, 2, 3, here we get instead the multiples of 2, 2, 4, 6, here the multiples of 3, 3, 6, so this matrix here is the multiplication table. If we want to get, for instance, F3, we will have the multiplication table 0, 0, 0, 0, 0, 1, 2, 2, and 4. So we will have the exponents of this divided by 3. So we have this exponential here, which are fractions of the complex circle, and obviously the 0 fraction R1, and this is the 1/3 of the complex circle. So it is here, and this is 4/3 of the complex circle, so it goes back to 1/3. So these two are equivalent, and let's see, they correspond to the value we have on the real numbers. We have the real part is -1/2, the complex part is square root of 3 divided by 2, so it corresponds to -1/2 plus square root of 3 divided by 2i, and this is the same. And then here we have 2/3 of the complex circle, which goes here, so we only change sign to the imaginary part, and we get -1/2 minus square root of 3 divided by 2 times I, -1/2 minus square root of 3 divided by 2 times I. And this is the quantum Fourier transform of order 3. We can do also the quantum Fourier transform of order 4, because it is even simpler. We have 1/2 and here divided by 4, and now we extend the multiplication table. 3, here we have 2 times 3, so we have 6, and 3 times 3 we have 9. We can write it as 1/2 times 1, 1, 1, 1, sorry, and here we get 1/4. Here we get 2/4, so 1/2. Here we get 3/4. Here we get 2/4, 4/4, so we are back to 1. Here we get 6/4, so 3/2, so we are back here. And here we have 3/4, so we are here. Here we have like that, and here we have 9, so we are here. And you see that this is even simpler than the quantum Fourier transform of modulus 3, because now here we get 1, 1, 1, 1. Here we get I, -1, minus I. This is -1, 1. This is -1, minus I, -1, I. And this is the quantum Fourier transform of order 4. Alright, now we can build our circuit. We start with only one digit, so that we understand how it works. We perform a Hadamard gate, so that it will go to 0 plus 1. In this part of the circuit, instead, we have our gate M. This is the state psi, which will be our guess. For now, now psi will be a superposition of all the possible eigenstates, but for now let's imagine it to be a particular eigenstate, because we want to see how the individual eigenstates will get entangled with these digits here. We do here a controlled operation. Controlled operation means that the operation will be done only if here we have the bit 1. If we have the bit 0, the operation will not be done. So we now have a superposition of 0 and 1, because we performed a Hadamard gate. And when we have superposition of bits, only the one component will get entangled with the operation. the zero component will not get entangled with the operation. So this operation, since it is an eigenstate of m, it will go to e to the 2 pi I theta of psi, and theta is the phase which we want to evaluate. So we have this phase shift only entangled only with 1, and we have no phase shift entangled with 0. So let's write here our total state. Here we have psi. The total state here is psi 0. Then we perform the Hadamard gate. We go to 1 over square root of 2 psi 0 plus 1. Then we perform the control operation. When we perform the control operation, it will only shift this by a phase, but the ket psi will remain. So it can still be written outside, but the phase shift will be present only in the one component now. So 2 to the e to the 2 pi I theta 1. So this is the state pi 0 which we get for now. Now we can't just measure the leftmost part, because we will get our eigenstate with 100% probability, and this will tell us nothing about the phase theta. So to measure theta we must measure here, but here we see that the rightmost component is 0 plus a number of modulus 1 times 1. So if we are going to measure this, we will get 50% of probability 0 and with 50% of probability 1. And this will tell us nothing about the phase. So we need to separate 0 and 1 even more, so that we get 0 times some coefficient which depends of theta, and 1 times some other coefficient which depends on theta, so that we will perform some measurements with some probability, and this will hopefully tell us something about theta. So here we perform another Hadamard gate, and so the state, we get the state pi 1 equals 1 over square root of 2 times psi, and the Hadamard gate here transform this in 0 plus 1 and this in 0 minus 1. So we get 0 multiplied by 1 plus e to the 2 pi I theta, and plus 1 multiplied by 1 minus e to the 2 pi I theta, and divided by square root of 2. So here we have 1/2 psi times this, and now we see that the coefficients are different. So they have different probabilities to be measured, because here the coefficients only differ by a phase, and if the phase is modulo 1, and the probability in the modulus squared, so it is 1 here, so 1/2 if you consider this, and 1/2 here. Instead, you see that now the probability to measure 0 is the modulus of 1/2 1 plus e to the 2 pi I theta squared, and the probability, this is the probability to measure 0, the probability to measure 1 is this, but with a minus sign, 1/2 1 minus e to the 2 pi I theta squared. You can factor out e to the 2 pi, e to the pi I theta, because the modulus of e to the pi I theta is 1, and then here you get modulus of 1/2 times e to the pi I theta plus e to the minus pi I theta squared, And here we get the modulus of 1/2 e to the pi I theta minus e to the minus pi I theta squared. So you see that you get the probability of 0 is the cosine squared of pi theta, and this is instead the sine squared of pi theta. And it makes sense because they sum up to 1 and the probability must sum up to 1. Now we draw a graph of the probabilities in function of theta. So the probability to get 1 is, probability to get 0 is cosine squared, and cosine squared looks like this. And here theta goes from 0 to 1. And the probability to get 1 is the sine squared. The sine squared goes like this. You see that for theta equal to 0, we have 100% probability to get 0. And for theta equals 1/2, we have 100% probability of getting 1. Now if theta is some other value, for example this or this, we expect here to have half of the times 1 and half of the times 0, but this is also the situation which we expect here, so we can't distinguish 1/4 and 3/4. On the other hand, if we know that theta is either 0 or 1/2, we will get the correct answer with complete certainty. And we don't need theta to be exactly 0 or 1/2, but it can be approximately 0 and approximately 1/2. We see that we will have probabilities of about 100% anyway. And this is the idea, to get a more precise graph which can cover also the other possible values of theta with certainty. Remember that we are trying to find a binary approximation to theta, and we have used only one digit. With one digit we can get either 0 or 1/2, so it makes sense that these were the only result for which we could distinguish theta. Now if we add another digit, we will get 0, 1/4, 1/2 and 3/4. So let's do that. Now we add another 0 here, and we create a superposition of 0 and 1. So we will have the state at the beginning it is psi 0, 0, then it is psi 1/2 psi, because we perform two Hadamard gates, 0 plus 1 times 0 plus 1. And you see now that expanding in the product, we get all the possible binary numbers. With the possible binary numbers with two digits, 0, 0, this time this is 0, 1, plus 1, 0, plus 1, 1. So this is why we are using Hadamard gates, because so we will get all the possible binary numbers within digits. Now you perform a controlled operation on the first digit and a controlled operation on the second digit. So you will get 1/2 psi times e to the 2 pi, sorry, the 0, 0, 0, 0 has is not entangled to any operation. 0, 1 is entangled to an operation on the first digit, 2 pi I theta, 0, 1 plus e to the 2 pi I theta 1, 0, and here we have e to the 4 pi I theta 1, 1, because here in 1, 1 we did the operation twice. What we want to do is to entangle the exponent with these digits. You see that here 1, 0 and 0, 1 are symmetric because we performed in both cases m once. What we should do instead is in the most significant digit we should perform m squared, because in this way here we would get 4 pi I theta, and here we would get 6 pi I theta, right? 2 plus 4, 2 for this digit and 4 for this digit. So what we see here is that we have entangled 0, 2 pi I, here we have e to the 2 pi I times 0 as in the exponent. Here we have in the exponent 2 pi I times 1, which is exactly this number here in binary, and here 2 pi I times 2, which is this number here in binary, and here 2 pi I times 3, which is this number here in binary. So in this way we exactly entangled the exponent with the digits. And in fact you can write this in compact notation as 1/2 psi times the summation on all the possible numbers x from 0, 1, 2, 3, but written in binary, from 0 to 4, from 0 to 3, all these binary numbers with coefficient e to the 2 pi I theta times x. Now they still have all equal probability because this is just a phase. So how to create different probabilities? Well, what if I show you now the expression for the Fourier transform, Fourier transform of order 4, 1/2 the summation of e to the 2 pi I x y divided by n times x y. Now can you see what will be the next step? Let me write f dagger, so the inverse operation. So we have a minus here, and let's apply it to a vector x. So here it will be the sum in y of this ket y, and we are in order 4, sorry, exactly, we perform f dagger here on the vector x, so that here we will get 1/2, sorry, now 1/4 psi times the summation in x and the summation in y of e to the 2 pi I x times theta minus y divided by 4 y. So from a uniform distribution of x, we arrived to a distribution on y which depends on theta, and we can calculate the probability to get each y. The probability to get some particular y is the modulus squared of this summation on all the x from 0 to 3 of e to the 2 pi I x theta minus y divided by 4 squared. If we now draw a graph of the probabilities in function of theta, we see that we have 4 peaks, one for each number from 0 to 3, particular for the number 0, for the cat 0, we have this peak, then we do something like this, and for the number 2 we will have this peak, for the number 3 we will have this peak, and for the number 4 we will have this peak. Basically inside here we have a sum with some destructive interference, and we are getting only one peak for each cat. Remember, all these exponential here are numbers on the complex plane, and when they sum vectorially here in the complex plane. So we will get the highest modulus when they all have the same phase. And for them to all have the same phase, we need the exponent not to depend on the x, on the term of the sum, so that they will have all the same exponent. And for this to happen, this will have to be 0, so that the exponent is 0 and will not contain x. So you will have theta equals y divided by 4. So you will have one peak for each y. For the cat 0, you will have one peak. Cat 1, you will have one peak at theta equals 1/4, and so on. For the cat 3, you have a peak at theta equals 3/4. This one here, and this one here is the peak for cat 2 at theta equals 1/2. And we are now ready to generalize our circuit. We will have m digits. We perform an Hadamard gate on every one of them. Here we have always our state psi, and our state will be psi 0, 0, and after the Hadamard gate it will be psi 0 plus 1, 0 plus 1, and so on m times. And this obviously will give us all the possible combinations with m digits. Now we want to entangle them in such a way that to the string x, for the string x we will have an exponent 2 pi I times x. To understand how to do this, remember that x in binary is some string with 0 and 1, and the jth digit will count as 2 to the power of j. It is like in base 10, but you replace 10 with 2, so you can write x as a summation of powers of 2, 2 to the k times nk, and nk is the kth digit. It can be either 0 or 1, and this exponent x means that you performed the matrix, the gate m, x times in total, and the jth digit will tell you that you have performed, that digit is entangled to the operation 2 to the power of j if that digit is 1. If that digit is 0, it is not entangled to any operation. So you have controlled operations which will entangle the digits 1 and with the exponent, and the jth digit will be entangled to the control m to the power of 2 to the j operation. So our circuit is like this. It has in the least significant digit to the power of 2 to the 0, so 1. Here it has control m to the power of 2, and then we have the third digit control m to the power of 4, and so on. The j digit will be m to the 2 to the power of j, and the last digit, the nth digit, the mth digit will be control 2 m to the 2 to the power of m. And I forgot to put theta here. And now we do, as before, the quantum Fourier transform. The quantum Fourier transform of order 2 to the power of m. So here we will get, here we had 1 over square root of 2 to the power of m because of the Hadamard gates, and after the Fourier transform we get another square root, 1 over square root of 2 to the power of m, and we get psi, and here we get the summation in y of e to the 2 pi I x times theta minus y divided by 2 to the power of m times y. Oops, I forgot summation in x and y. And so we can evaluate the probabilities to get a particular y, and they will be the modulus 1 over 2 to the power of m times the summation of these phases e to the 2 pi I x theta minus y divided by 2 to the m squared. So with these terms we have destructive interference except when y divided by 2 to the power of m is equal to theta. And so the peak for every y will be at y divided by 2 to the power of m. We will get 2 to the m peaks, each one separated of a distance 1 divided by 2 to the power of m, and each peak for each value of y. In particular, it can be calculated. I'm not doing it here, but I know there are some calculations which show that if the distance from of theta from the observed peak is less than 2 to the minus m plus 1, then the probability will be greater than 4 divided by pi squared, which is relatively high because it is about 0.405. If instead we have a distance greater than 2 to the minus m of theta, we will have probability 1 divided by 4, 25%, which is relatively low. If we run the circuit a relatively small number of times, we can get the correct answer for k. So we put ket1 in our circuit, which is a uniform distribution of the eigenvectors, and then we will draw random samples to get the least common multiple of all the possible k's, and we will have found our k. So this was Shor's algorithm for integer factorization. Quite spooky, isn't it? See you next time. It has been a pleasure.